All right, let's just jump right in. When you hear the word earthquake, it paints some pretty intense, right, even terrifying pictures in our minds. Giant cracks splitting the ground, buildings coming down, landslides. It's heavy stuff. But behind all that visible destruction is this immense, completely hidden tectonic engine right beneath our feet. And that engine drives one of nature's most fascinating forces. So, welcome to today's Explainer, where we're going to unpack exactly how this massive planetary engine actually works.
You know, what's truly staggering to think about is just the sheer volume of seismic activity on our planet. Roughly 1 million detectable quakes shake our Earth every single year. 1 million. Literally, the ground is almost always vibrating somewhere. Now, most of these are way too mild to even rattle a teacup in your cabinet, but it brings up the core question for this explainer. If the Earth is shaking this much, can we actually predict the dangerous ones?
So here is our roadmap for today. We'll hit 1. Earth's restless surface. 2. The tectonic engine. 3. Waves of destruction. 4. Measuring the shake. And finally, 5. Forecasting the unpredictable.
Okay, starting off with part 1, Earth's restless surface, finding the faults.
Let's establish exactly what an earthquake is at a fundamental level. At its core, it's just any sudden shaking of the ground caused by waves of energy moving through the Earth. Now sure, that energy can come from landslides, churning magma, stuff like that, but the crucial point here, and this is really how tectonic plates cause quakes, is that most of them originate at what we call faults. These are underground cracks where huge blocks of rock slide and scrape against each other. Some are tiny, smaller than your fingernail, while others stretch for thousands of kilometers. And it's absolutely no coincidence that the most active faults sit right along the jagged, highly friction-filled edges of our tectonic plates. Those massive slabs of crust are constantly grinding against each other as they slowly drift across the mantle below.
Which leads us perfectly into section 2, the tectonic engine, building the pressure.
Let's really zoom in on the exact mechanics here. How do drifting plates trigger such violent events? Well, because these tectonic plates are always moving, super slowly but constantly, they desperately want to just keep drifting. But intense friction keeps the jagged edges of the fault tightly locked together. So the plates keep pulling, but the edges remain totally stuck, and that puts this constant, immense stress on the rock. As that stress builds, the physical rock is quite literally being pushed, pulled, and sheared apart. It strains and bends. Eventually, though, brittle rock can only bend so far, right? Something has to give. The friction is finally overcome. One side of the fault suddenly slips, and all that pent-up energy just breaks loose at once. An earthquake is basically just the Earth violently relieving its own tectonic stress.
Moving right along this section 3, waves of destruction, how energy travels. So, what happens to all that energy once the rock slips at that underground hypocenter? It rolls outward in seismic waves. We have two main types of body waves traveling through the Earth's interior. First up are the P waves, or primary waves. These are fast. They compress and squeeze the material they pass through, kind of like if you pulled and released a slinky. They give you that initial jolt, but they usually aren't the main problem. Then we have the S waves, the secondary waves. These move slower, but they aggressively shear the ground side to side or up and down. And that harsh horizontal whipping motion, that is notoriously devastating, especially to older buildings that just aren't built to flex like that.
But wait, the real damage makers are actually the surface waves. These travel right along the top of the ground. Even though they're the slowest of the bunch, they produce this crazy, complex rolling motion. Imagine the ground moving up and down, back and forth, and side to side all at the exact same time. It's like a chaotic ocean wave, but made of solid Earth. That is what truly reshapes our world and causes catastrophic damage.
Now here's a really fascinating quirk about how this energy travels. Back in 2011, a quake in Virginia was felt over 600 miles away. Yet a much stronger quake in California was only felt about 250 miles away. How is that possible? Well, it all comes down to the age of the rock. On the U.S. East Coast, the rocks are much older, and the faults have had millions of years to heal up and solidify. This solid, continuous rock allows seismic waves to ring out like a giant bell, traveling huge distances. But on the West Coast, you've got younger, highly fractured rock and newer faults that just scatter all that seismic energy way faster.
All right, section 4, measuring the shake, the mathematics of magnitude.
Let's shift gears. How do seismologists actually calculate the total energy of these invisible waves? You've probably heard of the Richter scale in the news, but scientists today actually use an updated system called moment magnitude. Now, this scale is logarithmic, which sounds super academic, right? But it basically means the energy jump between numbers is exponential, and honestly, it's hard to wrap our human brains around it. So think about dry spaghetti. If a magnitude 4 quake is like snapping a single dry noodle, a magnitude 5 isn't just 2 noodles, it's like snapping 32 noodles all at once. And a magnitude 6, that's the energy equivalent of snapping nearly 1,000 noodles simultaneously. A single point increase means roughly 32 times more energy released. It's a massive escalation.
And to ground those numbers in reality, it really highlights why understanding these higher magnitudes is quite literally a matter of life and death. In 2009, a magnitude 6.2 earthquake struck L'Aquila, Italy. It brought roughly 20,000 buildings crashing down, claimed over 300 lives, and left 65,000 people suddenly without homes. It's just a tragic, sobering reminder of the raw power generated by this tectonic engine.
Which brings us to our final section, Part 5, Forecasting the Unpredictable, Science versus Certainty.
So that tragedy in L'Aquila actually sparked a massive global debate about risk. See, before the main quake, residents felt smaller tremors. A government commission told the public it was normal, but those shakes turned out to be foreshocks. Afterwards, an Italian court actually convicted several scientists of manslaughter for failing to warn the public, though, to be clear, those charges were later dropped after massive global outcry. And the scientific community was outraged because of the strict scientific definition of prediction. To actually predict an earthquake, you'd need to know the exact time, date, location, and severity in advance. And as it stands today, no one has ever successfully predicted an earthquake. Literally not once.
The reality is, small earthquakes very often don't lead to anything worse. And massive earthquakes can strike with absolutely zero warning tremors. You just can't know a tremor is a foreshock until after the big one already hits. So instead of predicting, seismologists forecast. Think of it a lot like a weather forecast. We can't tell you exactly when the tectonic rain is going to fall, but by studying seismic data, GPS, and geological records, scientists can forecast the probabilities over a specific time window based on the stress building up on a given fault.
Since we don't have a crystal ball to tell us the exact second that locked rock is going to snap, our absolute best defense relies on preparation. We deploy early warning systems, like the incredible networks in Japan, Mexico, and the US, that detect those fast-moving P waves and beam out alerts to your phone, giving you precious seconds to take cover before the destructive S waves arrive. We construct buildings meant to bend, not break. And for us individually, it means knowing your local risks and knowing exactly what to do the moment the room starts swaying.
Earth's tectonic engine never shuts off. The plates are drifting right now, the stress is building, and eventually that rock is going to slip again. As we wrap up this explainer, I want to leave you with this crucial thought. Science can give us the probabilities, but the rest of it is completely up to us. We cannot predict exactly when or where the next major quake will strike, but are you prepared for when the ground starts shaking? Thanks so much for joining me on this deep dive, and keep your curiosity as active as the world beneath your feet.